Hello and welcome to our webinar. This is part one of the RQ-30 webinar series, and we're really glad to have you join us today. We'll be starting shortly.
Yeah, I met Summermess Technique and became involved with them about 2013, 2012-13. They began developing this radar technology in around 2004-5. By about 2006, they had started to install them in the European market, Austria, Germany, Switzerland, places like this. And over the next number of years, it started to spread out across the world. I brought the instrument here to the United States in about 2013, began work with some very good people, John Fulton, one of them, and some others from the USGS over a number of years, had the systems approved, and have a lot of them installed now. And Summer particularly has now about 6,000 installed worldwide. Contact-free discharge measurement is an important method for measuring now. It's contact-free, so we have nothing in the water. There is no chance of the instrument being washed away, damaged by debris. And radar measurement itself is not affected by environmental conditions such as rain, temperature, humidity, and to a large degree vibration, unless it's incredibly severe. There is no calibration required for radar, and being, as I said, mounted above the water, it's maintenance free. So why we use it and the features and applications. So there's a range of services that use it for rivers, streams, mountain torrents, hydrographic services, civil protection. Agencies around the world are using it for flood warning and using its outputs to control where the water may flow through dams, through gates, etc. Civil protection, hydropower plants, and open channels, canals, drains, large pipe spillways. There's a whole range: irrigation, wastewater, hydro. So there's quite a range where this instrument can be used. So the RQ-30 and instruments that can calculate discharge like this, in this particular case, the RQ uses two radars, a level radar and a velocity radar, which we'll come to. And we continuously measure level and velocity. And the instrument contains a hydraulic model, and based on level, velocity, and some user settings and the model, it will calculate discharge on the fly. So contact-free, as we said, reliable, maintenance-free, safe from flooding, and it's fairly easy to install these on a bridge or arm. So the advantages of the system are it's a high reliability, the radar. It's fail-safe at floods, maintenance-free, so there's no fouling because there's nothing in the water, so there's no cleaning of the sensor and no risk of the sensor being damaged. Some of the very, very unique features that it has are due to the fact that we're measuring level and velocity continuously. This gives us access to data that you simply can't get by measuring level or with stage discharge ratings by themselves. We can see and observe hysteresis in the water, which I'll talk about. We can see riverbed changes, we can recognize vegetation growth that chokes a stream, and we can measure or see tidal effects. A conventional discharge measurement, the limitations of that are usually it's about money and time. I would say the gold standard is still a stage discharge measurement because it's repeated so often and checked so often, but it does have some limitations. And the manual measurements that are done using current meters or ADCPs are not always possible. There can be damage of instrumentation by bed load and trees and other instruments. You just simply can't put the ADCs in the water sometimes. It can be dangerous for employees in some cases. I've seen some very nasty incidents over my time in the industry where people have been hurt trying to make measurements in very high flows. And also the availability of employees to be able to measure continuously through high flow events. And the extrapolation of stage discharge at high flow, we just simply can't always get those measurements. So with a conventional rating curve, we have to do repeated measurements over time in order to generate our curve. And I'll show you an example of this. Whereas the radar, we can do continuous measurement and we can collect data very, very quickly. So this is an example of a river that we did in Malaysia, where you can see the red squares here were manual measurements over a 2-year period, and we could never get the high flows. It was always flooded. People couldn't get to the site. There were other reasons. Whereas the blue dots you can see here were collected once the RQ was installed over a 1-month period. So we can collect a huge amount of data very quickly. The measurement principle of the RQ-30, it uses 2 radars, as I said. One is a pulse radar or a time transit radar. So 26 gigahertz radar looking vertically straight down to the water, producing the level measurement. The velocity radar for flow velocity is a Doppler radar, so it's measuring the Doppler shift. It's at 24 gigahertz. And we're measuring, at that frequency, we're measuring the waves on top of the waves on top of the waves. So we're measuring the small waves that move with the water body about 3 millimeters, so about 1/8 of an inch. We measure the surface velocity, and from the model, we calculate the mean velocity and the discharge. Here's an example, a quick example of how the system generates discharge. So we have the 2 onboard sensors. We have the level radar and the velocity radar. We have a profile, which is a cross-sectional shape of the stream at the location we're measuring. And if we have that profile shape and we have level, then we have area. So we have our cross-sectional area. If we have local velocity, that is fed into the system, the RQ-30, and mean velocity is generated via the onboard model and some functions that the user can adjust. So if we have Q equals AV, we have our discharge. So this is a basic overview of how the system works. Now, I mentioned some of the really neat things that you can see with this radar in the data. We can see things such as hysteresis, riverbed changes, vegetation, and tidal effects, as I talked about before. And I'll show you an example here. This is simply this one, just to show how dynamic the radar is to measure compared to other situations such as ratings. So here we have very, very sharp increases in velocity and level, and the radar can track them very, very well. So we can have extremely quick rises of level and flow in the order of feet in short periods of time. And I'll show you an example of that in a short while as well. But yeah, it can handle very, very sharp increases. And you can see here, it's just going to give us a little area. And this is simply showing that we can do and develop a rating curve very quickly with high repeatability. This is an example here of flow hysteresis. So when we get an event and we get this energy in the water as it moves downstream, then what can happen is velocity will lead level. We'll have an increase in discharge, an increase in velocity for no change in level. And in this particular example, which I'll show you, we're going to be talking about this area between the dotted lines. This is a regulated river, regulated channel. And in this example here, we have level on the y-axis on the left side and velocity in green on the right. And so if we look at this timestamp of this area here, these blue areas here are separated by about 10 hours, and we're at the same level. But you can see on the rising limb of the event here, on the rising limb of the hydrograph, we have around about, I think it's about 7 feet per second. And you can see at exactly the same level about 8 to 10 hours later, we have a significant drop in velocity. And you can see it also shown here with a significant drop in discharge for the same level. This can be a very important or a very significant problem in forecasting some rivers, whether or not you're actually forecasting on the rising limb or the falling limb. And of course, you can see down here, if we plot level against discharge, we have our typical loop rating that you will see. We won't spend too much time on that, but I'm sure a lot of you would recognize what that is. And also this ability to be able to plot level against velocity gives us the opportunity to look at changes that happen in the water body. This is an example of what happened in one. We have done a project called the Anchor Project around the US with the NOAA Severe Storm Labs. And this was a place, it was a very, very interesting example that at this camp, which houses thousands and thousands of children, they had an event in 2015 which gave them a bit of a scare. Water came rushing down to a very mountainous area. The camp sits down below. And they had a level sensor, but they didn't get a lot of warning. It's very flashy. We installed the radar, or they installed the radar as part of this Anchor project just to look at this. And then this was produced, to give credit to JJ Gurley, one of the senior people there at the Severe Storm Labs. And JJ put this together, and what you can see here is that this event occurred and the actual velocity increased, the velocity and flow increased. He has nearly an hour here, 50 minutes to an hour before level even went up. And so this is an extreme case, but it's a real case, and it does happen in more places than you would think, where the measurement of level is not going to cut it in terms of having warning that flow has significantly increased. This is just an interesting article that's available online, showing here simply what I talked about, which is at the same level, we have an increase in velocity and discharge. Riverbed change is similar. I won't spend a lot of time on this, but because once again we're measuring level and velocity, there's a relationship created between these two, and we can see when they change, when they step out. You would still need to go out after and do a measurement, but you can correct in the radar. You're actually able to correct the cross section and actually recompute the discharge for the event. So we can see whether an event was a temporary, like scour and fill, where it was only affected for a short period, or whether it actually has been a permanent change to the geometry of the stream and therefore the discharge, the measurements. This is just talking about the recognition before and after the event. The radar can also measure supercritical flow. In this example here, we get a substantial rise in, a substantial jump in velocity with no change in level, and as shown in this example. So also we can spot vegetative growth that chokes the stream. So in this case, in early spring, here we're sailing along, we've got level and velocity moving together. And then in springtime, we get this vegetative growth and it starts to choke the stream. And it starts to dam up, level goes up, velocity goes down, and then at some point it's actually going to break up that relationship. We're going to get bad data, but it's a signature of this. They will send a crew out, they'll clean the debris out, the vegetation out, and we will return back to normal again. So that's another interesting feature that the radar has. We can also measure tidal, and this is an interesting site in Belgium. It's about 170 feet wide, and it's tidal, and it's the interesting thing about it is it's 80 kilometers inland, and it has a range of about a tide of about 14 feet. The radar's installed on this bridge railing, and what you can see here is the tidal influence, and we can actually even see the influence of the moon. But the measurement is going to be dictated on whether the tide is increasing or falling, whether it's coming in or going out. So this is another advantage of being able to use the radar, particularly for these tidal. We have a couple of examples around the world where they're close to the ocean and they have a treatment plant, and they want to know when the flow reverses, it's coming from the ocean upstream so that there's not too much salt gets ingested by the treatment plant. So that's just an example. There's no installation underwater, as we talked about, no construction in the river. You can install it all year round. We can mount the radar from about a half a meter, so a couple of feet above the water, up to 115 feet. We do now have a new model that's 250 feet we can go off the water. We're independent of flow direction. We can mount the unit looking upstream or downstream. We have mobile and fixed installations, and we can mount these on a bridge without drilling. They are safe from vandalism if you install them. Some cases it's a little difficult, but I think most of the customers that I've seen have been able to find a way to do it. Some examples here of some large cantilever arms, bridge installations, canal installations. This one's, I think, in Hong Kong. This is in Asia. This is in China. And this is in Europe. It's some different ways that it can be mounted. Now, something that's really important to understand is that if we're going to install a single sensor, such as the RQ-30, on a river, a stream, or a canal, there's an assumption that has to be made that there's a relatively even velocity distribution across that water body. If somebody else is joining late. If there is not an equal velocity distribution, then we've got a problem. We're going to have to find a location where there is. Because we're measuring surface velocity and converting it to mean channel velocity, then the assumption has to be made, or the site has to have a relatively even velocity distribution. If we don't have that, and we're on the bend of a river, really difficult hydrologic application, we've got acceleration around a bend of a river, we've got the confluence of two rivers, a lot of different scenarios, then we have a system called the RQ-30D. This is a multi-sensor system that will have one master RQ-30 and then one or more RQ-30s or just RG-30 velocity only sensors. You can have up to 8 devices on the one bus. They can be connected by radio or by cable. And in this case, as you can see, the channel is broken up into sections, and that's done quite easily in the software. And the unit will, in this case, use one water level, but it will use multiple velocities, and it will compute the discharge in each section and then combine those and output it. What's interesting about that too, we can do this on gates. We've done some spillways and dams where you might have 2 or 3 gates that are open, and we can actually compute discharge even though they're physically indifferent, they're separated from each other. This is an example of 3 units. Here we have the river in normal times, and then it will flood and go right across this, from one side or the other. This is just showing here how the cross-section would be broken up and programmed. This is a case study in Austria that was done. You can see here in this center picture, we have the main river here, and then we have another river coming into the side of it. We're on the bend, so we have this acceleration around the side. They had a tremendous amount of difficulty getting measurements here, and they wanted them and needed them here. They had tried in-water ultrasonics, the $80,000 to $100,000 systems, and they would get silted up, or they would have problems with them not being able to see because it would be so turbid. They eventually came to Summer. Summer put 2 RQ-30s in, and you can see the location of those here. This is a very wide section, about close to, I think, 1,000 feet. And they were able, with the 2 RQ-30s, to actually get very good measurements. They were asked, they had to do comparative measurements for the customer. They did those with ADCPs and with their own RP30, which is their mobile system, and the differences were very good. So that was an example of where the multi-sensor system can work. This is a crazy one. This is the largest one in the world, and I think it's the only one like this. This is a floodplain in Taiwan that's nearly a mile wide. There was no way for them to get measurements here. You can see it's just a horrible sight. So they actually put 2 8-sensor systems in. So there are 16 radars going all the way across here, joined together and computing discharge for the whole section when it floods. But that's an older system, and this has been installed, I think, probably for about 10, 12, 13 years now. Some applications, just showing again some shots how it can be mounted on cantilever arms, these massive ones that they have in China, some here, just different applications. We have this crocodile picture. Someone decided to put this in the presentation because this customer, and I believe this is in Australia, had just bought a brand new ADCP remote control boat, and an alligator, sorry, a crocodile took it. And I don't think they ever got it back. And so it was a little bit of a joke that if they, I don't know how you'd use a radar there, but watch out for crocodiles is probably the message. I'm going to cover this very quickly. We're about halfway through. Cover this very quickly. The RQ-30, its brother is the RP-30, and we've got a couple of pictures here in flood. This is the brother of the RQ-30 is a portable system that measures multiple velocities across a bridge using a bridge to do measurements, kind of like a current meter or a stationary boat measurement where you're measuring velocities all the way across, and it's used as a manual measurement from bridges by Summer and sells this instrument. So they use this instrument on the Rhine River here to do a comparison in flood, and this was a big flood, 2016, and so they were asked by the agency to do this because the agency already had an RQ there. This is the RQ right there, you can see. And this is just simply data which I could provide. I'm not sure people would necessarily want it, but it was just simply to show that the correlation. This is the output of the RP, which gives us our velocity profile and our discharge. And the measurements were very good. So in this particular case, the results were excellent. So I'll summarize again: contact-free, out of the water, maintenance-free, radar measurement, not affected by weather, continuous, so continuous amount of data at whatever rate a customer would want to measure, whether it's 2 minutes, 1 minute, 15 minutes, half hourly. Rating curve is not required for us to be able to install a system and produce discharge. We have recognitions of changes in the riverbed, and we don't have any limitations with regard to water depth. There is something a couple of things I'd like to cover, and then I'm going to open it up for questions. It's really important to know that this is not a silver bullet. It's really important to know where we can use this and where we can't use this. The system, the radar velocity, the level radar can see right down to zero. It has no problem. The velocity radar actually looks out at an angle of about 58 degrees, either upstream or downstream, and it's getting its echoes back. It's measuring its velocity by echoes returning off very small surface waves, ripples, pardon me, about 1/8 of an inch. If we don't have that, if the water is very glassy and we don't have much flow, we are not going to get a good measurement. So if somebody comes to me and they've got a canal, a river or whatever, and I look at some photos and that thing is moving incredibly slow or extremely glassy, straight away it's not going to be the instrument for that application. However, if there's an application where the river or stream does get like that, but only at certain times, and most of the time it is actually flowing and we can measure, then that's okay, because we do have some features on the radar where we can set low-level borders below which we won't use the radar's measurement. We'll use the internal rating curve to extrapolate the very low measurements down to zero. So it's not that we can't get data, it's just that we need to make people aware at those very low flows, it's going to be interpolated. Pardon me. And that occurs at about 0.5, 0.7 feet per second. So, you know, I've had measurements in concrete channels with 2 inches of water flowing incredibly slowly because it has riffles. I've also had sites where it's 1.5 feet and very difficult to get measurements. So it's site specific, but we don't need a lot of riffles. We just need some riffles. And that's kind of the takeaway. Apart from that, the other important thing is to note where you're going to install the system. We look for a decent amount of straight channel upstream and downstream. We don't always get it, and we've still been able to get good measurements when we don't. But the rule of thumb is we don't put it on a bend. We don't put it where we've got a bunch of rocks sticking up out of the water. We don't basically put it where we don't have a stable relationship between level and velocity. Having said that, we can actually put it into sites to determine if the sites do have a problem with their stage, with the relationship between level and velocity. So we do use it quite a bit to actually check sites and see what the relationship is and how stable that relationship is. So I hope that was helpful for you. I thought I would leave a fair bit of time and open it up for questions. I'm going to have a look at the chat window and see what we have here, see if I can answer some of these, and then I can actually unmute people if they would like to. Okay, well, I don't have any written questions, so if anybody has any questions, I'd be happy to take them. See if I can unmute everybody.
Hi, Peter. This is Frank Ingle calling.
Hey, Frank, how are you?
I'm good. How are you doing? I did want to ask, is there plans, or, we've discussed in the past about wind, dealing with correction for wind. And
yes.
Is there anything coming down the pipe from HSA or Summer on combining the wind? Yeah, sorry, go ahead. No, that's it. I'm just wondering about how to deal with wind and whether or not there's some sort of something coming that.
Well, we actually already have that and have had that for a few years now. It's the machine learning capability of the radar. And what I'm going to do is I'm going to exit out of this, excuse me, exit out of this presentation and actually open up the software. Actually, you know what, I'll show you something even more interesting. So while we were doing this work on the national water model, what we found was, if I can find it here, this is all to do with the national water model that we've been working on with them. And I'll have a look to see where I can see this. I have a screen, and David Maidman put this in. So this is an example. So basically, what happens, Frank, is that because every time the radar sees a level, a velocity, it sees an associated level. It starts off with 1, 2, 10, 100, 1,000, and usually takes several days to about a week and a half, as long as we have decent conditions for it to monitor. So it sees level, it sees associated velocity, and it begins to weight these, and it breaks up the level from 0 up to the maximum level into 16 bands. And when it sees these levels and these associated velocities, it weights them. And so after a period of time, it absolutely knows that it's mathematically impossible if for something to just throw a couple of, for example, for wind to come, or for a boat to go under, or for some environmental influence. And here, in this case, you can see this is the Cahaba River. It's a GS site that we did, but for the University of Austin. And here, the blue was this very noisy velocity, which was caused by wind at lower flows. And the machine learning, I don't have the left edge of the graph, but on the left edge, you would see that the machine learning starts, and it's, of course, trying to catch up. It gets noisy, and then all of a sudden now you can see it removes all that noise, and it's still very dynamic. It doesn't lose any of it. And so the only thing you have to do in order to turn this machine learning on is just to set a maximum water level so the radar knows what band it's going to measure between from 0 up to the maximum. But this is proved to be a very, very capable way of correcting for wind. Much better than all the testing they did was measuring wind at the site and applying corrections. This, to my knowledge anyway, this is what Summer, aside from this site, I don't know personally of other ones where customers have been using this, but at this site it worked brilliantly, and Summer tells me they have many, many stations around the world that use it. Does that answer the question, Frank?
Yeah, I think so. I think part of the issue for us in the USGS is that we have to have a documented method before we can adopt. So, like for instance, we can't use this particular method yet until there's a citable
Yes.
methods paper that we can call out as this is how it's being done, and
Yes.
That's part of our just normal fundamental science practice. So I get it. You're right. It looks great, and eventually we'll be able to use it or figure out something, I guess.
Yeah, and I think Summer has been very open. We had some meetings with senior people, and Summer was very open to being able to share their black box, if you like, technology with the GS under a privacy agreement, and be able to show them what they're doing and how they're doing it, so it could actually even be used or modified by the USGS.
Yeah.
So we understand that they won't take somebody's necessary black box. I mean, there are many agencies around the world that do, but I completely understand the USGS's position about wanting to, be able to scientifically see what's being done and how it's being calculated. And the same for discharge. But, when we do install sites, if a good location is picked, we usually get very good results, unless there's some sort of issue with the setup, the cross-section, or it's not a great site. There is quite a bit of fine tuning you can do with the RQ-30, so we can, models change at particular levels. We can fine tune it by, if we do an ADCP measurement, for example, we have a reference discharge tool where we can actually add those reference discharges and pull the internal rating curve that's calculating discharge into alignment with that. So it does have some nice new features. There is some new graphical software coming out in the next several months, and there is also going to be some new features on the radar. They haven't told us what. They're kind of keeping it under wraps, but the new software I think is going to be really nice and more user-friendly. I mean, I don't have any trouble. I'm used to it, but I know first-time people, when I'm showing them, it can be a little daunting.
Thanks, Peter. I'm encouraged to hear that the work to develop like a CRADA or something like that is still ongoing. Appreciate the answer.
And it would be with you guys, the Surface Velocity Users Group, and other people and other customers, or particularly you guys, because this is your business. And I'd really like to see those discussions, move forward. And I think that's got to be done at a high level. So, for example, you guys, the user group, and Summer, to see and develop a process for being able to do this, sharing the technology, doing some testing and whatever else you would need, and even making corrections or adjustments for the USGS to do it a certain way, or a particular way that was better for you. But we've had very good success with it, and for many agencies around the world, they're happy to roll with it. I don't know if anybody else has any questions.
Yeah, Peter, can you hear me? This is John Fulton.
Hey, John, how are you?
Good. How are you doing?
I'm good.
So, good. Yeah, very good presentation. Thank you. So the question I have regarding the delivery of spectrum, right? One of the things that I think would be super helpful is that when we take measurements, we can sort of spin test them based on the spectrum that's collected.
Yes.
And I know, if I understand right, the MRL7 has that capability.
Yes.
So is there, one of the challenges we have is, with, the whole cellular network in terms of what protocol the MRL7 operates under. So is that something that, I know years past, there was an intent to develop both CDMA, which is, sort of Verizon based, and GSM, which is AT&T based, but now maybe with the, the 4G capabilities, that's no longer a necessity. So is that true? So if we were in an area that is predominantly, sort of more heavily covered by Verizon, do you know if we acquire an MRL7, it can operate under Verizon, sort of like coverages?
Yes, mate. Yeah, we do. We will have, or do have, I think it's already done, have a, I think it's it may be just being tested, but I was told that we do have a dual band modem, so GSM or CDMA, TDMA, Verizon, AT&T. So yes, that's available. It's true that the summer logger does have direct remote access into even radar spectrum, being able to turn this feature on. And I'm showing for the benefit of other people what that would look like. And actually, what I'll do might be even useful. Let me go open the actual software and show what it really looks like.
And Peter, while you're doing that, I have, I guess, another question for you in that regard. And I do want to sort of emphasize, I think, we've talked about this before, and Summer, Christoph, and Wolfram, and yourself have been very, very open with how it operates. So I think we would like to enter into some type of an agreement. I think it would be helpful because there's things that we could share with you and you with us, which I think would be mutually beneficial. So if you have a chance when you talk with Christoph, if they would be interested in engaging in that kind of an agreement, it's pretty easy to set up for us at least. And I think it would be super helpful. One of the things we're really trying to push is ensemble approaches. So if we had a discharge that's derived from the Summer algorithm and we use our PC algorithm and they both have sort of converged in the same number along with the PID computation, it really brings credibility to the discharge estimate. And I think that's important, particularly since we're really beginning to spin up more and more of these sensors across the US. Having the ability to have 3 discharges that all sort of point in the same direction would be super valuable.
Yes.
The other thing is that have you shared with Richard Pardee or anyone at the HIF the MRL7 to see if we could get it integrated into our, kind of into one stop?
We haven't, but we should. We were marching along really well, and then this whole drama that started with COVID-19 has stopped things like traveling there and meeting them in person and discussing stuff, and it's made it a little more difficult. But we would definitely like to do that. There's a couple of points about that. It's a fully integrated logger with that radar. So you can connect the radar up to that logger via 485, and it gives you direct access remotely into the radar, all its functions: parameterization, viewing of spectrum in real time, programming changes, editing profiles and uploading them remotely, firmware and software upgrades, anything. And we do have, 4G, that's 3G forever, but 4G, AT&T and its supporters, and now Verizon. So the other thing is that the ADMS, which I'm not sure if you're aware of, let me just see if I have, I think I have let me go to our website. You are familiar with the ADMS, John?
I am not.
Okay, so it's an RQ-30 in a single housing, very much like the RQ-30, except it has battery, MRL7, antenna, everything. And the only thing you need to add is a solar panel if you're going to exceed the battery's limitations, which can run, I think, depending on measurement time, for several weeks. And it looks like this. So you can see it looks very, very much like the RQ-30. It's slightly bigger. But so this is everything: battery, logger, antenna. This is the planar antenna for 4G. So that's something that we've put out a few, flyers and newsletters and stuff like that on. But that's just something to keep in mind. It may not be, it's obviously not going to be of interest where you guys want to have your own station and send the data over GOES and all of that. You'd want the RQ because it's a single instrument. But this is a good option for like rapid deployment and things like that. The only thing I would add to that is if it's going into permanent installations and you want to access it, not for servicing, there really isn't any, but for, I don't know, there might be cases where you've got to replace the battery. You want to check that it needs to be, it needs to be somehow accessible on an arm that can be lifted up or moved. you need to be able to get access to it. But it is a really nice compact option.
Okay, no, that's great. Thanks so much, Peter.
Yeah. Does anybody, are there any other, I just got to cover this if people are interested. This is an example of a spectrum. Now, I was going to connect up to a live radar, I didn't. But what this is showing is here, each time a measurement is performed, and the radar, the velocity part of the radar is doing hundreds of measurements over its measurement time, measurement duration. And it's producing a spectral graph or an analysis or a record of the returned energy and the velocities it's calculating. The y-axis here is amplitude, and across the bottom we have actually velocity. Everything inside the colored section is being used by the radar to calculate the measurement. And it sees velocities. As you'll see here, it sees lots of velocities. Even when water is flowing, looks fairly uniform and it's raging down, we will still see flow in opposite directions, swirling. The radar knows by a setting there, if we tell it that we're measuring and it's only flowing downstream, then it can ignore anything that it measures. You can see there's a little bit of backflow that it's, opposite direction content here, but it will ignore that. And then this line that it sees and that it creates in the middle here, that produces our velocity. And we have a quality value that comes with every one of these. It is on the output string. And I didn't cover the output string. That's kind of for the next one. But we output level, velocity, discharge, area, and some learned values to do with the machine learning, learned velocity and learned discharge. So the quality value, the third parameter, is very important because we know straight away whether we're getting good echoes. And this is just a representation. And here you see we have 11. And if I go back, they color code each one differently so you can analyze them. And you can see in this case, this is extremely repeatable. And also for analyzing and for troubleshooting, if there's an issue at the site, maybe it's parameterization, maybe it's not good flow, whatever, that we can have someone do this and just save these in a file. They're just saved and then be emailed to us and we can look straight away. There's a lot of information we can glean from this.
Thanks for joining us today for part 1 of the RQ-30 webinar series, and we look forward to seeing you on a future webinar. Bye for now.